Assalamualaikum warahmatullahi wabarakatuh. To my panel 1, Dr. Azia binti Kamis, my panel 2, Dr. Khairul Azmi bin Baharin, and my supervisor, Dr. Chim Kingan. I'm HADIZA binti Muhammad ARSAU. Today I would like to present my final year project 2 entitled System Performance and Economic Analysis for Solar System in UTeM under Net Energy Metering, which is NEM. This presentation consists of Chapter 1 Introduction, Chapter 2 Literature Review, Chapter 3 Methodology, Chapter 4 Result and Discussion, and lastly Chapter 5 Conclusion. Net energy metering or NEM is a practice where energy produced from the solar PV system installed will be consumed first and any excess to be exported to the official distribution licensee, which is Tenaga Nasional Berhad, TNB. However, by end of 2020, the Malaysia government has introduced NEM 3.0, where several new initiatives has been introduced to increase investor interest in participating in the NEM program. The new initiative is NEM Rakyat for domestic, NEM Government for government building, and NOVA for commercial and industry. The quota allocation for NEM Rakyat is 100 MW, for NEM Government 100 MW, and NOVA 300 MW. The difference between NEM 2.0 and NEM 3.0 is NEM 2.0 explain 1-to-1 offset will occur in 10 years and doesn't state what will happen after 10 years clearly. But for NEM 3.0 clearly show that 1-to-1 offset happen for 10 years and after 10 years will be converted to selco. Self-consumption or known as selco occur when electricity is generated for self-consumption and any surplus is not allowed to be exported to the grid. Next, this is the quota balance and quota applied for NEM Rakyat, NEM Government, and NOVA. As we can see, the quota for NEM Rakyat and NEM Government is still a lot, but the quota for NOVA is dwindling. This shows that the commercial and industrial field are taking good opportunities provided by the government to help increase the use of renewable energy in Malaysia. Next, methodology. The research process starts from identify the existing problem for the purpose of identify the realities of the project. After identify the problem, a site assessment was carried out. Analyzing resources, load profiling, and system design is implemented after the site assessment is done. Finally, find the solution to the problem in this project. Electricity consumption is one of the causes of the increase in CO2 in addition of transportation, waste, and other development. Carbon emissions are from the process of producing electricity, and this means that the less electricity used, the less CO2 is released due to it. In this table, this is the example of energy consumption in UTeM. As we can see, the number of energy consumption is higher every month. As discussed earlier, the available capacity for commercial and industrial is 1 MW peak or 75% of maximum demand. The table shows the maximum demand in UTeM in 2019. As we can see, the higher value is in April, which is 5,691. The average of maximum demand is 5,259. So that means we can apply the capacity less than this number. In NEM, the equipment design, installation, testing and commissioning, and the operation and maintenance of the solar PV installation shall comply with the energy laws and any other relevant legal that have jurisdiction over the installation and operation of the solar PV installation. The figures show the example of connection to TNB. This method is adopted for net energy metering and self-consumption scheme. Power consumption and export are measured by meter 1, while power generation is measured by meter 2. For net metering, meter M1 shall have bidirectional capability to register the import and export units. Meter M2 is dedicated PV meter to record the generation from the indirect PV generation system, and all costs relating to the PV meter shall be borne by the customer. Under NEM 3.0 program, the credit to the NEM consumer shall be based on prevailing energy rate in kilowatt-hour in the gazette tariff for the NEM consumer. Net change amount is equal to energy imported from distribution licensee times prevailing gazette energy rate minus energy exported to distribution licensee times prevailing gazette energy rate. The table shows the tariff C1, which is medium voltage general commercial tariff that UTeM use. For all kilowatt-hour is 36.5 cents per kilowatt-hour, and for each kilowatt of maximum demand per month is Rm 30.3 ringgit Malaysia. My objective 1 is to design the system of solar PV system in UTeM. In site assessment, I will discuss about OSH risk, shading analysis, PV module selection, inverter selection and other consideration. The study area conducted in Melaka is located at latitude 2.267 and longitude 102.25. The table shows the irradiation that Melaka receives every month. On average, Melaka receives a total of 1,660 kWh per meter square of solar energy each year. Next, OSH risk. Safety and health risk in the workplace is very important. The common risks in this study are falling from the roof during installation, electric shock, injuries from lifting the installing heavy modules and inverter, and last but not least, injuries due to falling object. Next, shading analysis. Any object that cause a shadow on a site during a clear sunny day will affect the potential power output. The example of shading analysis is natural landscape, tree or other vegetation, other buildings and part of the same buildings. So, we need to avoid installing PV module at the shading area. Next, module selection. The choice of PV module depends on several factors such as temperature consideration, available area and maximum system voltage. The weather in Malaysia is never too hot and temperature range from a mild 20 degrees Celsius to 30 degrees Celsius. And this is suitable for monocrystalline module. As we know, monocrystalline module has a higher efficiency compared with the other modules. The installation of modules on the roof is limited, therefore usually high efficiency modules are used to ensure maximum output. The maximum system voltage for this module is rated at 1000 volt DC. The figure shows the data sheet for monocrystalline module that has selected in this analysis. The available area rooftop in UTeM is FKE building, FKEKK building, Sport Complex UTeM building, FTMK building, Cafe Plaza 1 and Cafe Plaza 2. The total area is 9,319 meters square. This is the location and top view of the UTeM roof space. The estimate distance of roof is measured by using Google Maps. Next, determine maximum number of modules based on area. There are two ways to install the PV module on the rooftop, which is portrait and landscape orientation. Usually, we need some space around the perimeter of the roof and also need to consider gaps between modules. In this case, I assume 2 cm of gap between modules and 0.5 meter spacing around the edge of the roof. So, in this table, show the total module that can be installed in the rooftop is 4,873 pieces of modules. Next, inverter selection. In system design, balance of system, which is BOS, is one of the important parts that we need to be focused. There are three types of inverter, which is modular, string, and central. In this study, I was selected string inverter. There are many things to consider in choosing the inverter, which is peak rating of PV array. For string inverter, whether to use single or more than 1 MPPT, type of shading, capital cost, and average annual energy yield. The figure show the data sheet for string inverter that selected. Next, matching PV array with inverter spec. The maximum number of modules for one inverter is 25 modules and the minimum number of modules is 8. Next, the maximum number of string in one inverter is 3 and the maximum number of modules is 127 modules. After design the module and inverter, the expected number of modules is 4130 and the number of inverter is 36. Next, system protection. Firstly, bypass diode. Voltage rating is 74 volt, current rating is 11.18 ampere. Second is circuit breaker. DC rated trip current is 16 ampere. The DC voltage rating is 133.2 volt. Next, for cable sizing, the minimum size cable is 2.5 mm square. For ADC cable is 1.262 mm square. Next, maximum voltage drop. For DC voltage drop is 22.5 volt and for DC power is 193.54 watt. Okay, next, other consideration, which is location of system equipment. Another factor that needs to be considered is the selection of the location of the system equipment such as inverter, array junction box, and combiner box, and nets meter. In addition, the selection of the point of common coupling, which is PCC area, is also important in the study. PCC is the meeting point between the solar system and TMB. For example, the selection of area to place DB, MSB, and substation. Second, cable route and length. The purpose to identify the location of all equipment is to estimate the length of cable that is used in this solar system. The cable length to estimate include the distance of the solar array to the junction box and the junction box to the inverter or direct solar current to the inverter. In addition, the distance between the inverter to the switchboard or distribution board and the distance from main switchboard to net meter. My second objective is to analyze the economic of solar PV system in UTeM under NEM 3.0. The analysis consists of demand and solar irradiation profile and economic analysis. Next, UTeM energy demand. Maximum demand is one of the important components in billing system of electricity consumption of consumer. Maximum demand is measured in kilowatt and monitor for half an hour each month. The average UTeM demand is 5,259 kilowatt. Next, UTeM energy demand. It can be clearly seen the highest demand is on weekday from 8 AM to 5 PM. This is because during that time period, a lot of load are applied. On weekday, the demand is seen be quite low because students and staff are not in UTeM. In light of this, it can be concluded that on weekday, the energy generated by solar PV system could be exported to the grid as demand from UTeM was low during this period. Next, solar irradiation in Melaka. As can be seen, March is the month with the highest level of solar radiation. On average, Melaka receives a total of 1,660 kWh per meter square of solar energy each year. This value can be also called the annual peak sun hour. As discussed in graph 2, the annual irradiation in Melaka is 1,660 kWh per meter square per year. So, the peak sun hour that Melaka receives is 4.55 kWh per meter square per year. Next, system performance. After consider all losses factor, the total system performance is 0.7936. Annual energy yield can be calculated by using rated power times irradiation time losses. In this study, the PV capacity that was assumed is 950 kilowatt peak. So, the annual energy yield that can produce is 1,251,507 kilowatt hour. Next, specific yield. The specific yield is used to compare the performance of PV system for different technologies and different areas. So, for this system, the specific yield is 1,370 kilowatt hour per kilowatt peak. Next, performance ratio. This ratio is used to assess the installation quality. For this system, the performance ratio is 0.7936. Next, simple payback period. The table shows the key parameter and assumption used in this study. The proposed total PV capacity is 950 kilowatt peak for an area of 9,319 meters square. This analysis estimate the price per kilowatt peak is 4 ringgit Malaysia. So the estimate system cost is 3.8 million ringgit Malaysia. So the estimate yearly electricity bill offset is 456,800 ringgit Malaysia, and simple payback period is 8.3 years. Next, levelized cost of energy, LCOE. The concept of LCOE is to measure lifetime cost divided by energy production. The function of LCOE is to measure value across the long term, showing project life cycle costs to highlight opportunities for tribes to development different scale of projects such as facility, community and commercial, and to inform they should pursue project on the economic basis compared to utility rates. In this example of calculation, a 950 kilowatt peak on-grid PV system project with 4,130 modules with each module rate at 235 watt peak is suggested to install in UTeM under NEM. The estimate startup cost is 3.8 million ringgit Malaysia, and the levelized operation and maintenance cost is 50,000 per year. For example, this project estimate finance with 3.8 million, 20-year loan and 7.5 interest rate. From the calculation, cost of PV electricity is 23.5 cents per kilowatt hour. For LCOE calculation, the electricity price is 29.75 cents per kilowatt hour. Compare then C1 tariff, which is 36.5 cents per kilowatt hour, so that the cost of PV electricity is lower than C1 tariff. My last objective is to study feasibility of implementing solar PV system in UTeM under NEM 3.0. A graph shows a monthly comparison between the energy generated from the 950 kilowatt peak solar system and energy used by UTeM building. As can be seen in graph, the study found that the profile of solar generation is much lower than the energy used by UTeM. The solar generation profile generally coincides with the demand profile. However, only about 10% of the UTeM electricity use can be transferred by the proposed 950 kilowatt peak solar. But referring to the electricity consumption at UTeM over the weekend, the data show a decline in terms of energy consumption and maximum demand. The capacity of proposed solar system is higher than the demand. Therefore, over the weekend, it is hoped that the surplus solar energy will be able to export to the grid to be offset. An example of data taken in January 2018, where the average energy consumption is 13,777 kilowatt hour compared to the solar energy produced is 105,548 kilowatt hour. In conclusion, the solar NEM program is economically attractive to implement at UTeM. UTeM will enjoy an offset 1-to-1 rate for 10 years and subsequently get electricity bill saving through the concept of self-consumption after the expired of the period. UTeM is one of the beneficiaries of the NEM 3.0 program because the installed PV system is able to generate a lot of energy on daily basis. With the installation of this PV system, UTeM is able to save at least 10% of electricity from the grid. That's all. Thank you.